You have already read all the instructions, and we will follow the same instructions say throughout the SEM. Now we start with our first topic. Okay, that is symmetry as per discussed. Now I am sharing with you a screen. Say can you see anything?
Yes, sir.
Yes, sir.
Yes, sir.
What? PowerPoint presentation?
नो सर,
No.
ओनली ओनली ये
Only
टीम्स दिखा रहा है कुछ सब।
only teams दिखा रहा है. Okay. Now can you see PowerPoint presentation?
Yes, sir.
Yes, sir.
Yes,
यस
sir.
सर।
Yes, sir.
And can you see do not copy so that I can confirm whether it is the same PowerPoint or not? Right? Okay. So let us begin with the same. We will start statistical mechanics. Good. Are you recording? Someone is recording? I am not recording. So please someone record it if possible. Okay. So we will start with the statistical mechanics. Say you can simultaneously write down your things. First of all, Bose-Einstein and Fermi-Dirac distribution functions. So generally you are aware about different types of functions. So these two are special functions. For certain particles, Bose-Einstein functions are valid, distribution is valid. For other types, Fermi-Dirac distributions are valid. Okay, so we will see in future that which type of particles obey Bose-Einstein and which type of particles will obey Fermi-Dirac distribution functions. But the basic construction is the same. So now can you see 8.1 symmetry functions slide?
नो सर।
No,
No,
sir.
sir.
Can you see 8.1
No.
symmetry of wave functions? Huh?
No, sir.
सर
Any
8.1 पर क्लिक करो, स्लाइड ऊपर करो थोड़ी.
symmetry of wave functions? Can't you see?
No, sir.
Okay. When? Now, can you see?
Yes, sir.
Yes, sir.
Okay. So now this is our first topic, symmetry of wave functions. Okay. Let us take some say example of a gas system or anything. The system is made up of a n number of particles. Within the enclosure, there are n number of particles. Let us suppose that we are choosing only one particle within the system. Okay. So this is a closed system. It may be open system. So it may be canonical, grand canonical or micro canonical ensemble as per SYBSC. Okay. Anything. So within that ensemble, let us select our first particle A. Now if this is the particle, then the particle certainly possess some type of energy, which is the combination of total energy and say part of it is kinetic energy and potential energy. So we can say that it is in the energy state. Let us consider the first particle A. So it is in the energy state nth. Suppose this is the particle A, it is in the nth energy state. Okay. So we can characterize a wave function which is determined by the Schrodinger equation. You had studied this Schrodinger equation. Schrodinger equation is there, and the general formula of the Schrodinger equation is H psi it is equal to E psi. So here you can see the first equation. It is H psi A n it is equal to E A n psi A n. This is the first equation of our 8.1. Okay, but this equation is valid only for a certain types of boundary condition depending on our problem. Okay, so up till now clear? Can you hear and see simultaneously?
Yes, sir.
Yes, sir.
Okay, so now we proceed. The energy associated with this particle A, it is known as eigenvalue. It is known as eigenvalue, and we can represent the same eigenvalue by E and A. So generally I will speak N as a subscript and A as a superscript. So first is subscript and second as a superscript. Okay. So psi Na is the function and its eigenvalue is E and A. Now, instead of particle A, if there is the another particle within the same enclosure, say particle B, I am reminding you there are n number of particles. So now we talk about the second particle B. It is in the energy state K. Again, it is possessing some type of kinetic energy and potential energy. So it possesses total energy, say E. Its function would be represented by psi kb, just like the previous one, psi na, and the energy by ekb. So now we have both the particles within the systems. If both the particles are present simultaneously within the system and they do not interact, be careful, if they do not interact, then this situation can be represented by the eigenfunction psi Na psi Kb according to equation number 2. Okay. So we have the first equation is the Schrodinger equation H psi Na equal to E psi Na. That is the Schrodinger equation for the combination of both the particles. When both the particles are present simultaneously, we have psi Na psi Kb equation number 2. Okay, so we have two particles now within the system. So automatically the enclosure contain a total energy which is equal to ENA plus EKB. So that is the total energy of the particles or the system if there are only two particles. Now let us say that if we interchange the particle, or let us say that in a better way, if we interchange the energy of the particle after the interaction, okay, after the collision, then the particle A possesses the energy of the K state and B possesses the energy of the N state, like that. After interaction or after changing the particle, both the particle possess vice versa energy. Okay, so now up till now, say before that, we have the total energy ENA plus EKB. After exchanging the particle, we have now another wave function where the particle A is in the K state and B is in the N state. Wave function can be represented by psi NB psi Ka according to equation 3. Okay. Now, what about the total energy of the particle? Total energy of the particles or the system, it can be represented by, say, instead of this ENA plus EKB, now we have the total energy ENB plus EKA after interchanging the particles. Now let us say that within the gas system, suppose there are only one kind of particles, say heliums only. Okay. So now if there are two particles of helium, we cannot say that this is the particle A or particle B. Because if we close our eye and open our eye, then it is impossible that the particles may change their places or not. So we can't see or we can't distinguish the particles. In this situation, the total energy of the particle, it is ENA plus EKB. Before exchanging the particle, it is equal to ENB plus EKA after exchanging the particles. So in both the conditions, the total energy of the enclosure is the same according to equation number 4. Okay, understood up till now?
Yes, sir.
Yes, sir.
Okay, so now we proceed. Any questions?
Sir,
If you have questions, then you
sir,
can write it down in your notebook. We will discuss afterwards. Okay. Now, let us say that before exchanging the particles, we have the wave function psi Na psi Kb. But now, after exchanging the particle, the wave function is psi Nb psi Ka. And both the wave functions are not same. Okay, because we know that the particles are interchanged, yet we cannot distinguish the particles, and so the energy will remain the same and they are in the degenerate states. Okay, so after exchanging the particle or before exchanging the particle, since the energy remains same, the system is degenerate. Most general wave function obtained by taking the linear combination of all these particles, n number of particles. Now up till now we have assumed only two particles. So we will take the example of two particles. So two combinations, particularly for the two different particles of the same kind, is very simple. It is number one psi Na psi Kb plus psi NB psi Ka. So this is the addition of both the situation. So we have situation number one, before the plus sign, original, after the plus sign, after interchanging the positions of the particle with respect to energy state. If both the wave functions are added to each other, the situation is known as symmetry. Whatever the result of the linear combination for the eigenvalue, the result will remain the same. There is no change at all. And so this type of functions are known as symmetric wave functions. Now let us say that after the exchange of the particle, we have the situation just like according to equation 2. Psi Na psi Kb minus psi Nb psi Ka. In this situation, again the energy remains the same. But what is happening? The spins of the particles are changing. Okay, let us say that the combination of these two wave functions before the interaction and after the interaction, the linear, see, you can see the arrow. This psi nb psi ka changes its sign, and hence we can represent the same equation number 2 by a determinant. So we have the determinant psi na psi nb. This is the first row of the determinant. Psi ka psi kb, the second row of the determinant. So we have the multiplication, cross multiplication, psi na psi kb minus psi nb psi ka, and since the minus sign is there, the wave function is anti-symmetric. The wave function is anti-symmetric. If a and b are interchanged, number one, the first equation, that means with the positive sign, first equation, it remains the same. There is no change at all. But the second equation contains a negative sign. Okay. So whatever the energy value is there, for the first condition, before exchanging the particles, the same condition will be there as far as energy. So absolute value of the function is unaffected, but only the sign reverses. So this type of function is called anti-symmetric. Okay. So this is symmetric function with the linear combination of two particles, and anti-symmetric function with the linear combination of the two particles. Clear? Hello?
Yes, sir.
Okay. So now next, we it may be noted that, or we may note, the equation 2 and 3 neither symmetric nor anti-symmetric. Which are the equations 2 and 3? Equations 2 and 3, this is the equation 2. Say psi na psi kb, that's all, nothing else. So before the exchange of the particles. And the next equation, equation 3, psi nb psi kA. Okay, so these are two individual equations. So these equations are neither symmetric nor anti-symmetric. But if we take the linear combination of these two situations, then they are symmetric and anti-symmetrics. So independently, equations 2 and 3 are neither symmetric nor anti-symmetric. Okay, since interchanging of a and b transform the wave function into one another, that's all, nothing else. We are writing a and b, yet we cannot distinguish them. So they are changing into themselves only. Okay, but in the linear combination, we are getting, say, symmetric and anti-symmetric wave functions. Now we will expand our view for the n number of particles. So suppose there are capital N number of particles, A1, A2, An, and that A1 is in state N1, A2 is in state N2, and similarly An is in state An. Okay, Nn. So all these particles are different energy states. So there are n number of particles, A1, A2, and like this, and there are, say, energy state E1, E2, E3, En. So the wave functions which corresponds to these distributions will be, now let us say that this is the original wave function. Okay, just like equation number 2. It can be represented by psi n1 a1, psi n2 a2, psi nn an according to equation 7. So here this is the original situation. Now let us say that only one particle is interchanged with the other particle, or say two particles are interchanged with other two particles, or say all the n particles changes their position. So any interchange in the distribution of n particles in the n state entails a change in the wave function. So wave function is different. It is the different situation that whether they are symmetric or anti-symmetric. Okay. So that will depend on the linear combination. That will depend on the linear combination. After interchanging the particles, the wave functions will change. So we can say that in equation 7, suppose A1 and A2 are interchanged and other remains same. So we have the new wave function psi n1 A2, psi n2, so n2 A1 and so on. Say psi n3 A3, others will remain the same. So after interchanging any two particles or any number of particles, the wave function will change. Okay. So we have different wave functions. So there is a change in the wave function. Since the total number of different distributions with one particle in each state is n factorial, there are n number of particles. So let us exchange the first two particles and the new system is generated. So it is the second system. Let us exchange second, say third and fourth particle and the new system. So it is generated. In this manner, we have n number of different situations. So there are different n number of different wave functions of the type 7. So we have the type 7. I have given the example just now that the second situation is psi N1 A2, psi N2 A1 and rest of the terms are same. So similarly, let us say that the next situation is psi N1 A2, psi N2 A1, the next psi instead of psi N3 A3, now we have psi N3 N4 A4. So in this manner, we have total n factorial number of different wave functions of the type 7. They are neither symmetric nor antisymmetric. Now we can take the linear combination of all these n number of wave functions. So in general, we have only one equation of a linear combination. So among the linear combinations that may be constructed out of this equation 7, we will get two different situations obtained by adding n number of different particles, n number of different states, energy states, and so n factorial fundamental situations. So number one situation, it is sigma psi N1 A1, psi N2 A2, and in the similar manner up to the last particle psi say NN AN. So this is our first. Then sigma I equal to, say it will run from 2 to n again. We will have, say, the second term psi N1 A2, psi N2 A1, and rest of the terms are same. So in this manner, we are taking the linear combination and our combination, it is known as sigma. It is the summation of all these different types of terms. So this is equation number 8. And since they are containing only positive signs, we cannot distinguish the particle. These functions are known as symmetric wave function. The second situation, where we have negative signs for the half of the function within the same ensemble. So let us say that if we gather all these terms, then we have the determinant, which is the anti-symmetric determinant, and the determinant is psi n1 a1, psi n1 a2 up to psi n1 an. So in short, we can say that all the particles are in the state n. Okay, n. So this n, it is equal to n1. That means all the particles are remaining in the same energy state n1. The second situation, psi n2 a1, psi n2 a2, and so on. So this is the second situation, and so on. In this manner, we will get the anti-symmetric function just like equation number 9 or the situation 2. Now we have the wave function. We know that we can normalize the wave function. This thing you had already learned, say in the quantum mechanics. Okay, so we can normalize the same wave function by multiplying the same linear combination by 1 upon under root n factorial. By 1 upon under root n factorial. So this is normalization constant. Okay, we will take in solid state the example of the same normalization constant. So at that time you can understand how can we generate the same equation. So the wave function will be normalized by multiplying the linear combination of the same or the wave function by 1 upon under root n factorial. Now a wave function determines a microscopic state of the system. Okay, so let us say that we have linear combination. So each term in the linear combination will give one microscopic state. So there are n number of microscopic states. Different types of wave functions therefore will lead to the different conceptions of the microscopic states. Okay, so here only locations are changed, nothing else. The total energy of the ensemble will remain the same. So thereby we will have different types of statistical mechanics. Okay, so these different types of statistical mechanics will give different things. It will give different things. So now, up till now, do you understand everything? Hello?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So now, say we will see slightly how can we share or how can we interact with each other. Okay. So let us say, can you see my screen, Microsoft Team?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Now,
Yes, sir.
do you have any questions regarding this? Any questions? Suppose we consider a function psi. Okay. We have the, can you see the screen, white screen?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
Yes,
Yes,
So
sir.
sir.
here we are considering the wave function psi. It is in the energy state n. Okay. Let us say that within the energy state n, there is a particle A. So our wave function will become psi n A. Okay. For the first
Yes,
particle.
sir.
Similarly, now we have the another particle, the wave function psi. Okay. With the state k. But now within the state k, we have the particle B like this. So we have the total wave function psi Na and psi kb. Okay, both the particles are present within the system. Now we interchange the particles. That means this will lead to our new system, new wave function. And new wave function, it could be represented as psi nb like this, and then psi, say k a in this manner. Okay. Now since we cannot identify A and B or B and A, since both the particles are same. Okay. So situation 1, this one, before the arrow and after the arrow, after interchanging the particles, since we are unable to distinguish between B and A particles, particles are only there. So we cannot identify the particles. So both the wave functions look the same. So this type of wave functions are neither symmetric nor anti-symmetric. But certainly we know that the positions are changed. Okay. So this is the first situation before the arrow. This is the second situation after the arrow. Now we have the another system. Say, let us say that psi n a, the system is like this. Psi k b in this manner. Okay. Now let us say that if we consider our ensemble, then after interchanging the particles, we have the total wave function, which is known as the linear combination or the general combination of both the situation. So it will give the total wave function in this manner. Okay. So this is our total wave function. Okay. So the total wave function I have written in the next line. It is equal to psi Na psi Kb plus psi Nb psi Ka, like this. So this is the total wave function. But now here the total energy of the system, it is as for example E in this manner. So this is the total energy of the system. Okay. Let us say that we have the different situation like this. So the second situation is in this manner. Psi, say N A, psi psi, say in this manner. The situation is like this. So after interchanging the particle, we have another combination of the wave function according to third row. Okay. So this function again, the energy will remain the same, E, like this in this manner, but the wave function is anti-symmetric. But the wave function is anti. Okay, clear?
Yes, sir.
Okay. So different number one, say the symmetric wave function, number two, anti-symmetric wave function. Now we can generalize the same system and we will get the equations like this in this manner. According to equation number 8 and equation number 9, using the system for n number of particles. Okay. So here in the number 9, half of the terms are with negative sign, half of the terms are with positive sign. Okay. Just like the third line. Can you see in the white paper? Hello.
Yes, sir.
Yes, sir.
So this is the presentation, say PPT. Say here we can see equation number 8 and 9. Can you see those equations?
Yes, sir.
Okay.
Yes, sir.
So we
Yes, sir.
can generalize the system in this manner. Okay. Now we have symmetric wave function, anti-symmetric wave functions. Hence, the further development for the calculations are different one. Okay. So now I think we can switch over to whiteboard. Say easily. You can see it and we can do the same thing. Say very easily. So are you comfortable with this type of say conditions? તમને ફાવે
Yes,
છે
Yes,
આ
sir.
sir.
રીતે બધાને
Yes, sir.
Yes, sir.
બધાને તો આપણે થોડીક સ્પીડ વધારીશું નેક્સ્ટ ટાઈમ થી. ઓકે. આ આપણો ઇન્ટરેક્ટિવ
Okay, sir.
સેશન છે. પહેલું માઇક્રોસોફ્ટ ટીમ્સ થી અવગત થવા માટે થોડું જોવા માટે માઇક્રોસોફ્ટ ટીમ્સને સાથે સાથે કોઈ ટોપિક ચાલુ કરવા માટે. બરાબર છે? ઓકે. તમારે અત્યાર સુધીમાં ઘણા લેક્ચર થયા હશે. બરાબર છે? તો આજે જે રાઠોડ સાહેબનું લેક્ચર છે, રાઠોડ સાહેબનું લેક્ચર છે એ એમણે કેન્સલ કર્યું છે. ઓકે.
Okay,
Yes,
sir.
sir.
Okay,
હા,
sir.
કારણ કે એ વખતે એમને ખબર નહોતી કે પંડ્યા સાહેબ લેક્ચર લેવાના છે. તમારો ડેટા લિમિટેડ હોય છે એવી કમ્પ્લેન છે. બરાબર છે? એટલે એમણે પોતાનું લેક્ચર આજે સ્ટોપ. પંડ્યા સાહેબે જે સેટ કર્યું છે એ એઝ ઇટ ઇઝ રહેશે. આઈ થિંક 10:30 નું છે. બરાબર છે?
Yes, sir.
ઓકે.
Yes, sir.
હવે હા તમને સ્ક્રીન દેખાય છે. બરાબર છે? પટેલ રોશન કુમાર છે કે?
Yes, sir.
ઓકે. બીજા કોઈએ જવાબ નથી આપ્યો ને? હા. હવે થોડાક ટાઈમ માટે તમારા વિડીયો ચાલુ કરો એટલે હું સ્ક્રીનશોટ લઈ લઉં. કેટલા જણા હાજર છો ટોટલ? બધા જ એવું નહીં. હા. 1 2 3 4 હજુ ધ્રુવી દરજી ભાર્ગવ કુમાર પીએસ. ઓકે. બધા એક સાથે આવો. રાઈટ. એ હજુ છે બીજા કોઈ જેને બાકી હોય વિડીયો ચાલુ કરવાનો? જેટલા હોય એટલા ચાલુ કરી દો એટલે એક સાથે હું એક જ સ્ક્રીનશોટ લઈ લઉં. દરજી ભાર્ગવ કુમાર, કેન યુ હિયર? માઇક ચાલુ નથી એનું.
Yes, sir.
સો કેન યુ સ્વિચ ઓન યોર વિડીયો?
Yes, sir. અવાજ છે પણ દેખાતું નથી.
મને દેખાતું નથી એટલે. બરાબર. ટોટલ કેટલા છે એક્ટિવમાં? 1 2 3 4 5 6 7 8. આનો
સર
વિડીયો બને.
સર
નવ.
મારો સર તમે
હા,
મારો ફેસ
બરાબર.
જોઈ શકો છો?
પછી પીએસ કોણ છે?
હેલો સર,
હા.
તમે મારો ફેસ જોઈ શકો છો? કેમ કે પીસી યુઝ કરું છું ને એમાં કેમેરા વર્કિંગ નથી એવું બતાડે છે.
નહીં તિવારી પછી કેટી
હેલો
પણ
સર.
Yes, sir.
હા ટોટલ 9 દેખાય છે અત્યારે મને.
ચાલુ જ છે, but થોડું દેખાતું.
સર
સર
મારો દેખાય છે, હું આર્યન પટેલ છું.
અત્યારે ચેતન સુરેન્દ્રનાથ નો વિડીયો બંધ છે.
સર પીસી માં ઓન છે એટલે પીસી માં કેમેરા વર્ક નથી કરતું.
નો પ્રોબ્લેમ એટ ઓલ, બટ યુ કેન કન્ટિન્યુ વિથ યોર મોબાઈલ એપ ટુ. એમાંથી ચાલુ કરીશ તો દેખાશે. બરાબર છે, કઈ વાંધો નહીં, નો પ્રોબ્લેમ એટ ઓલ. બરાબર.
સર આર્યમ પટેલ છે, દેખાય છે મારો વિડિયો?
એક મિનિટ. પહેલા હું સેવ કરતો જોઉં. જસ્ટ અ મોમેન્ટ પ્લીઝ વેઇટ. હજુ પણ 9 જ છે. બીજા કોઈ છે?
સર છું સર
હા.
છે અમે.
સર આઈ એમ
છે.
વિશાલ.
હા, બરાબર છે.
સ્લાઇડમાં
શું?
મોડું થાય યાર.
હા, મને મોડું થાય છે. ચાલો, ઓકે. તો આ જે છે એ બરાબર છે, બધાને બરાબર લાગે છે?
સર
આ
મારો
રીતે
ચાલુ
હા,
નથી આવતું.
અધિકારી
Yes, sir.
Sir,
ચેતન.
there are
ઓકે.
34 participants,
સર નથી આવતું.
but it has limit, so
ઓકે, બરાબર છે. કૃતિશ કુમાર, રાઈટ?
કૃતિક સર.
હા,
સર
ઓકે.
sir,
Vera. હું સ્ક્રીન શેર કરવાનું સ્ટોપ કરું છું. ઓકે, લગભગ બધાના આવી ગયા છે. જો ના આવ્યા હોય તો પણ વાંધો નહીં. બરાબર છે, ના આવ્યા હોય તો પણ વાંધો નહીં. બરાબર છે. આ આર્યન પટેલ.
સર સર
હા,
Yes, sir.
સર મારું નામ મોવલ્ય છે. ફેસ દેખાય છે?
શું કોણ છે?
મોવલ્ય
અવાજ નથી સંભળાતો. આઈ થિંક સ્ક્રીન શેરિંગ બંધ કરું છું હવે. અત્યાર સુધી કોઈ પ્રોબ્લેમ તમને?
No, sir.
કોઈ પ્રોબ્લેમ નથી ને?
No, sir.
નો સર.
નો સર.
જસ્ટ અ મોમેન્ટ. તો આ રીતે ફાવે છે ને?
Yes, sir.
હા,
યસ સર.
ઓકે. સો આઈ થિંક that's all for today. બરાબર છે. હું શેરિંગ બંધ કરું છું. તમે જોઈ શકશો હજુ. ફક્ત શેરિંગ બંધ કર્યું છે મેં. switch off your videos. No problem at all. બરાબર ડેટા બચાવવા માટે થેન્ક યુ વેરી મચ ઓકે નાઇસ ગુડ બાય
થેન્ક યુ સર.
સર રેકોર્ડિંગ મૂકી દેજો.
હા
રેકોર્ડિંગ મૂકી દેજો એમ.
હા હું ટ્રાય કરું છું મેં કર્યું તો છે પણ હજુ એટલે શું થયું છે એનું મને ખ્યાલ નથી પણ તમારામાંથી કોઈ કરે પણ છે